Hello, everyone. Good afternoon. I'm Bikram, and today I will be presenting my project on adversarial attacks on time series. Time series classification models have been garnering significant importance in the research community. However, not much research has been done on generating adversarial samples for these models. These adversarial samples, they can become a security concern, as we have seen in this class where adversarial attacks have been used to attack LLM models. In this topic, we deal with adversarial samples attacks in time series data. With time series data, network packets are also similar as they arrive in a timely fashion. And network packets, they are also susceptible to attacks from foreign elements like hackers. So when we're dealing with time series data, this kind of work, they can be extended to adversarial attacks in other forms of data which are of the type of time series. While running the code, we obviously will face significant challenges. And similarly, while running this GitHub repository, I face significant challenges, which I will show in my demo. But first, let's discuss the challenges. The first and foremost challenges what I faced was the TensorFlow version. The code which I worked with was a really old code, almost 5 years ago. And that time, the TensorFlow version was the version 1. Currently, we are running TensorFlow version 2.15.16, and which is a very new version. So many functionalities which existed in the old version, they don't even exist now. So to even get the base code running, I had to change a lot of functionalities, which was a significant challenge, understanding those functionalities and figuring out the new functions which existed with the TensorFlow version. The second challenge which we faced was understanding the various metrics which came with the data, whatever the results was there, understanding the significance of those results. Since we needed to change for this project, it was important to understand the overall code structure, which was also a significant challenge given the complexity of the code structure. And finally, last but not the least, the running time of the code was also significant, because that gave us the time that how much time we are taking to run the code and get the results before understanding what are the flaws with it. So it was also the running time also posed significant challenges, and sometimes we had to run with less epochs or lesser model complexity to get the results on time. Before moving on to the actual code, I will give you a brief demo of the workflow of this code. First, we have our training sample, which is defined by X true or Y true samples. Then we pass it to through a gradient adversarial transformation network, which is a network defined by the researchers, which is able to generate adversarial samples for a particular class as defined by the user. We call that X adversarial. Then we pass this the true samples as well as the adversarial samples separately through a classifier model, which gives, for the true samples, we get Y predictions, and for the adversarial samples, we get Y prediction adversarials. And this is where we made the changes. So for the classifier model, the researchers, they tested just with CNN model, but in my case, I not only tested with CNN model, I made the change to add the test with LSTM models also. Some terms which will come later into the explaining of the code. One of them is the mean squared error. That's the difference between the training sample and the adversarial sample. The second is the train accuracy realistic. This is the accuracy between the true Y values and the predicted Y adversarial values. So basically, the actual ground truth as well as the predicted values from the adversarial samples, the accuracy value is defined by the realistic accuracy value, and the optimistic accuracy value is defined by the predicted adversarial values and the Y predicted values, which we get by running the true sample on the classifier model. Then there is the train target rate. That's the proportion at which adversarial samples are misclassified into the target class, and the number of adversaries, that the number of samples that were correctly predicted initially, but they were changed by the adversary. We now move into the demonstration of the code. When you open my GitHub repository, you'll get something like this. First, I have clearly mentioned what steps are involved in running this code. And if you follow these steps, you can clone the repository, you can get what the requirements are by running this code, as well as how to obtain the datasets. The dataset has not been provided into the repository. The reason being that the dataset size is huge and you need to manually download the zip files. And I already have the unzip the Jupyter notebook, which will help you unzip the code. And this Jupyter notebook, the specialty is this one has the password which is required to unzip the folder. I actually had to solve a puzzle to get this password. And thanks to Alex, who helped me actually solve this puzzle to get the password. Other than that, the steps are provided into for training and evaluating the model, both the CNN and the LSTM models, and how to visualize the data. So moving on to the demonstration of the code. So this is the repository which I cloned from the initial one. And I can show you where the changes have been made. Here, as you can see, that these changes are basically not the changes for improving the code. These changes are changes which occurred with the TensorFlow version. So this was the initial one. And later I had to add this file at this line instead of the initial one to get this code to run. So there are several points where I had to make the changes, and which took a really long time because to understand the point where the error is coming. The changes could be as simple as this. This was the original one which occurred with TensorFlow version 1, where it's mentioned Adam optimizer, but with TensorFlow version 2, you need to mention that it's keras.optimizers.adam, not .adam optimizers. So these kind of changes, it took while it might look simple, it took significant amount of time to identify those changes and make the proper changes at proper positions of the code in this file. So other than that, we have the white box pie, where in the base file, this is the initial fully convolutional network, which is defined by the researchers. And where I made my change, I have mentioned the modified code where I have defined an LSTM network. As you can see, my LSTM network is not that much complicated. The reason this is because LSTM is taking a really long time to run, and it runs for 300 epochs for each hyperparameter. So to run that, it takes a really long time. So I didn't have the liberty to give higher and make more complex networks as with the CNN, as with the LSTM. So I contended with only 2 LSTM layers of very small 32 and 16 units, whereas the CNN model, they were able to use 128, 256, and 128 units for this CNN layer. But other than that, even if you have powerful GPUs, you can try with complex LSTM networks, and that will work. And it probably might give you better results with complex LSTM networks. But this is a major change which I made, and the comparison can be obtained between the CNN and the LSTM network. So running this, we can run this. As you can see, this is running only for 10 epochs. This is because the initial training is for 300 epochs, which takes a really long time. But once it has been trained, the weights are stored, and only 10 epochs is required to retrain the model once the weights are saved. So this will finish quickly, hopefully. and we can get the result. This is for every beta, but you will obtain the results something in the log files, where this is for the CNN model, and you will obtain results something of this kind, where you can get results for one data set, as many data sets as you want to mention. And basically, what I mentioned previously, the mean squared error, the accuracy realistic, the accuracy optimistic, the target rate, and the number of adversaries that were changed by the adversary, that were classified correctly previously, but were changed by the adversary. And similarly, for this will run for a little bit. So, this model this is running is for the initial code, which initial CNN model, which is provided by the researchers. And in a minute, I will show you the code which is actually which I wrote, and what are the effects. And the effects I can show you here because I have the results. This is for LSTM, and clearly it is not, it won't running for every data set takes a lot of time. So I was only able to run for 2 data sets. And since the LSTM models is not that complicated, the mean squared error, the values didn't come. But it's not that if you make the model complicated, you will get the mean squared error, where the adversarial samples, they are better and better adversarial samples. So it's not that the results are not coming. It's just that the model is not that complicated because of the CPU processing issues with my computer. So the main difference we need to see is that for the LSTM network, there were a lot of classifiers which correctly classified previously, but they were changed by the adversaries. So the adversarial network, they were able to fool the LSTM network more than the CNN model, because in CNN model, you can see here that for the dataset 21, you can see that initially it was misclassified, and those stayed the same. So as well as for the, yeah. So initially it was initially it was classified correctly, and those were misclassified by the later by the adversary. And also you can see by the train target rate, which as I mentioned previously, the proportion at which the adversarial samples are misclassified into the target class. So that is high. So almost all of the samples, they got misclassified into the target class once we ran the adversarial samples. So yes, so this search was completed. So this occurred for the CNN model, and for the LSTM model, this is the whitebox new.py, which will run for the LSTM model. And the LSTM model, as you can see, this will take some time. This takes a little bit more time than this. Other than that, you can also run the evaluation. So running the evaluation code, this is the code for testing. Here you can add the various data sets which you like to test, but currently this is for shortage of time. For the demonstration, I'm showing only for one data set. This code whitebox.py, this is for the CNN model, and the whitebox new.py is for the LSTM model. As you can see that it was successfully tested for the CNN model, as well as for the LSTM model. You can successfully test. And it's imperative to mention that I can test it while the LSTM model is running in parallel, but in real life, when you are running, first you need to train the model first using the training sample. And after that, using the search file, after that only you can run the evaluation file. As you can see, the results have come in very quickly. And yes, there are the number of adversaries which were initially classified correctly, but then they were misclassified. As you can see, the trained target rate is high. So you can see that the model was able to fool this LSTM model very easily, as well as for the CNN results. I can see that not for all cases, it was not able to fool it perfectly. There were cases where it was able to fool the CNN model only partially. And we can observe a change in results when we make the LSTM model more complex with powerful GPUs that can be tested later, but not with this CPU. And finally, what I want to show, there is a visualizer script where you can give a data set and you can give a specific sample ID and which you can run and it will give you the visualizer of the time series data which was obtained. So here in the images, you can go and I think you can get one sample like this, where the real sample is like this, and then there exists adversarial sample. So you can get results like that, where you can see that what changes the adversarial samples has made from the real one. So you can visualize the data to see what is going on with the real one and what is going on with the adversarial one. So with this, I conclude my presentation. Thank you. And any question you might have, it's welcome. Thank you.